Today I'm going to explain you my code in my Matlab. This is the 6 methods on finding the root. So the first method we're going to explain is the root. It's going to be the bisection. So this is my code. Then first, here, this is the user input step size. Then here, the user input tolerance. Then here is the user input iteration. Max iterations, I mean. So here is call helper to find all roots using the bisection method. Then here is the display results. Display results is here. And show also the iteration table and plot the result. Going here, in this code right here, this breaks the interval into segments and applies bisection where sign changes are found. The root list indicates store all unique roots found, and the logs stores all iterations data. Now here high is equals to minute. Ensure that we don't overshoot. Going here, this apply bisection only if sign change, indicating a root in the sub-interval. Also here, it is to avoid storing duplicate roots within the tolerance. The logs accumulate iteration logs. Then here, please move to the next sub-interval. Going here, it performs the actual bisection algorithm on the sub-interval. Then here, this log iteration data, low, high, mid, f of low, f of high, and f of mid. Here, this one. Then here will be the final approximation of the root. This one. Then below this one will display tabular data for all bisection iterations. I think that's all for the bisection method. Now going to the next method, the graphical method. Here is to estimate roots of a function within a given interval using graphical analysis, enhanced with sign change detection, root refinement, and clustering. This one is default number of points if not provided. And here is the default tolerance for root proximity. Going here will be the evaluate the function at evenly spaced points in the interval. This one will be identify indices where sign changes occur, potential root brackets. Then here, step 2, this one, it is to define brackets between sign changing points. Also refine root location using a basic bisection method. In step 3 here will be add points where the function value is very close to 0. And here is to prevent adding duplicates by checking proximity to known roots. Into step 4 here is to combine close roots using clustering and return their average. Now for this one is to display summary of detected roots. Now going down here, it is the plot to plot the function and highlight detected roots. Now going here, this one is to refine the root using bisection until tolerance is met or max iteration is reached. I think that's all. I mean it's not all. Going down here, this is the group nearby roots and average them to eliminate duplicates. And this one, add last cluster, start a new cluster here, then finalize, add a current group here, and that's all for the graphical method. Now let's go to the incremental method. Now we are here in my incremental method. So this find roots of a function using the incremental method. So interval start and range over which to serve for the roots. This will be the user input, step size, and tolerance for identifying the roots. This root list is to initialize list to store detected roots. And here will be the generate x values based on steps. This one for storing data about each step. And here, define a subinterval x lower and x upper for root checking. And then here, if f this is to check for a sign change, approximate root using midpoint. And also sign change detected. To also handle near zero function values at boundaries. Then near zero at left boundary, near zero at right boundary. And going here will be the no root in this subinterval. So this is the formula here. Now this one will be the avoid duplicating roots by checking proximity to existing ones. Now here will be the store data for this interval in the log. Here will be my print root summary. It will display the summary. Then this one will be the table of search details. Going to the figure, this is where the plot the function and mark detected roots. Then this is where the plot roots found, where it will be highlighted. And I think that's all for the incremental method. Now let's go to the Newton method. Now here in my fourth method, which is the Newton method, this one here is to define step size, tolerance, and maximum iterations. Display initial configuration info. In this one, this is to estimate all roots within the given range using the Newton rhapsody. Here will be my display roots found. And this one right here, over here, this is the plot, the function curve, and roots. I'm going down here. This one, this one, I forgot. This is it performs Newton rhapsody from a single initial guess. Now from the break here, it will avoid division by zero. This is the this one right here is the formula of the Newton-Raphson. Here here is the calculate approximate relative error. In the rows is this is the store iteration info, and this one stop it will stop if error is within tolerance. And this one prepare for next iteration. Doing here will be to return final estimate if max iteration is reached. Now here in this code, it will scan a range of initial guesses to find multiple distinct routes. It will also tag all iteration data with the initial guess. Also store route only if it's unique within the tolerance. And here will be the last part of the code. We'll check if a route is unique based on proximity to existing ones. That's all for the Newton-Raphson method. Now let's go to a regular pulsar. Now here's my regular pulsar method code. This is my parameters: step size for dividing the interval, then error tolerance for converge, and maximum number of iteration. This one is to attempt to find all routes in subintervals using the regular pulsar. This one is to print configuration details and display the route summary. I don't need to explain this one. Then this one right here, xy, is to plot function and then identify routes. I'm going to the function right here. This one, this is to divide the interval into smaller subintervals. If a sign change is found, then apply regular pulsar. In this, it is to check for root in A and B using sign change or small value at endpoint. For this one, this is to store root if it's not a duplicate. This one. Okay. Going to the next function. This is to apply the regular pulsar algorithm to a single interval A and B. It also stops once converge criteria is met or max iteration is reached. Here is to ensure there's a sign in A and B. Now this one is to avoid division by zero. Here is to compute a new approximation using regular pulsar formula. And here is to calculate approximate relative error. This one right here is to save current iteration values, and this one is to check for convergence. Down here will be my update interval depending on sign of f of a multiplied by f of c. And that's for my regular pulsar method. Now let's go to the last method, which is the second method. Now we are here at my final method, the second method. The main function of this is to find the roots of the function f using the second method within the interval x range, x minimum and x maximum. Reports root found, prints an iteration table, and plots the function with roots. This one right here, the roots. And then this one is to hold all iteration logs to print it later. This one unique roots found. This one is Just call helper function to scan the interval and find roots. And then let's go to the function. I don't need to explain that here, right here. It's the same at the top. And the xbox here, this one is to generate points to form pairs. Now, for this one is to run the second method for each pair of initial guesses. This is to check if found root is unique and add it to the roots list. Now for the other function right here, this one will perform the second method iteration starting with x0 and x1. It returns the found root and log of each iterations. Right here is the each row stores iteration data. This one is to avoid division by zero. This one right here, it is to calculate approximate relative error in percentage. Now here will be the log iteration data. And this one also is to check if approximate error meets tolerance to stop iteration. Then here, update x0 and x1 for next iteration. Here will be if the tolerance is not met, return last computed x2 as a root. This one last to x2 value. Then for the last function, checks if any newly found root is unique by comparing with previously found roots within a tolerance. And here, then this one is distinct from all existing roots. I think that's all. That's the final method. Now let's try running the program. Running the code. Here in main, you need to run. Then enter a function. Let's do a basic one. Start point and endpoint. Also, you need to select one method by entering the numbers. Let's choose the graphical first. There you have it. The roots are found, which is a -2 and a +2. And this is your graph. This is my graph. Now let's do another method. There you have it, the incremental, your graph, and the iterations. Now let's do the other one by section. Let's do -5 and 5 here by section. Okay. There you have it. Now, 4, 5, and regular file size 4. There you have it. Now let's do another one. Let's do the Newton-Raphson. And there you have it. 6 methods of finding the roots. Go to the final method, which is the second method. Let's try running it. So the start point will be 1, and 5, 6. There you have it. That's all 6 methods of finding the root using Matlab.